Great. Thanks so much. So thanks a lot, Yang Yang, for the very nice introduction and for the invitation to speak in this seminar. So I took a look at the website for the seminar, and I'm very honored to give a talk among such distinguished speakers. So thanks so much. It looks like a really exciting seminar. So today I'll be talking about sort of like a body of work that I've been doing in the past couple years in my research lab and also with several collaborators at different places about basically offline and online learning in this predict and optimize setting. So I just want to acknowledge first my collaborators and also the papers that this talk is roughly based on. So this body of work sort of started with a collaborator of mine, Adam Elmachtoub at Columbia, where we wrote the sort of first paper on this topic. From our perspective, the Smart Predict and Optimize paper was published recently in Management Science. We also had several follow-up papers, and I especially want to highlight this last paper and also my student Heyuan Liu. So Heyuan just graduated, was a PhD student with me, and his work, he really did some really great work in this space, and in particular, this last paper, which I will describe in detail in the second half of the talk, was really driven by his work. So I just want to especially acknowledge him, but also all of my other collaborators. Great. So let me give the sort of outline. So basically, I'll start by discussing this predict and optimize framework and some preliminaries. I'll then talk about sort of how we do optimization for learning in this framework through a surrogate loss function approach. Then I'll talk about some statistical results that we developed in the offline setting, in particular risk bounds for this surrogate loss function. And then I'll move on to this more recent and exciting online setting about how we do online contextual decision making and basically the corresponding theory of regret bounds that we developed. Okay, and please feel free to interrupt with any questions at any time. So let me start with a description of the sort of framework and basic preliminaries. So the motivation for this body of work really comes from the observation that in many industries, large-scale optimization problems that are being solved for decision making almost always involve some unknown parameters. And many industries, many companies are using machine learning or statistical estimation more generally to somehow estimate these unknown parameters. And often there's some relationship between the unknown parameters and some contextual or auxiliary data, right? So that's sort of where the machine learning comes in, is we try to build a model that uses these features about contextual information to predict the parameters of the optimization problem and then correspondingly solve the problem to make decisions. And so this is, generally speaking, often why companies will hire people that, are both interested in machine learning and also people who are, interested in optimization, because really they're doing both of these things together in tandem. Right. So sort of the classical approach here is that, given historical data, we'll build a predictive model, a machine learning model from the data in a way that is sort of totally blind, totally agnostic to the downstream optimization task, right? So we separate these two phases of prediction and optimization by first building the model for predicting the parameters in some traditional ways, and then we plug in those predictions into the optimization model to make a decision, right? And so this sort of, classical basic approach of separating prediction and optimization, it suggests that, there's an opportunity for us to do better by somehow using the information about the downstream optimization task to inform the prediction phase, right? So somehow, if we can use the structure or the information about this downstream optimization problem as part of the learning phase, maybe we can do better. And before I talk, about some ideas along that direction, let me give a couple of more concrete examples. So think, for example, about vehicle routing or simply a shortest path example. So like a platform such as Google Maps or Waze that is giving routing recommendations to drivers. In fact, they give many, many recommendations throughout the day to different drivers. Fundamentally, we all know that they're solving a shortest path problem on a network in order to give these recommendations, right? Uh, However, the exact edge costs on this network, which are really the travel times along different roads and different segments of the network, the exact travel times are actually unknown at the time of when the platform has to give its recommendation. Instead, they're making predictions for these travel times, perhaps based on features like time of day. If it's 9 a.m., we expect more traffic than at 1 p.m. And also information about the weather, whether there's construction happening on the roads, and so forth. Right. So these sort of contextual information, which is available, can be used to make predictions about the edge costs, the travel times on the network, which are then fed into an optimization solver. In this case, a pretty simple optimization solver. It just solves a shortest path problem, right? So this is one sort of straightforward example. Another example is in finance, right? In portfolio optimization. So think about the returns of multiple assets, let's say D different assets, which are unknown but may depend on contextual features, contextual information like the historical returns, news headlines, economic factors, social media, and so forth. All of this kind of external information people are trying to use to make good predictions for asset returns so that they can make some money. And so ultimately what they're doing is they're making predictions of these returns and then solving an optimization problem to determine an optimal portfolio. And usually this kind of optimization problem has some sort of constraint or some sort of consideration on the risk of the portfolio. So let's say the covariance matrix of these returns is actually known, and we can model that in the constraints. Then we can formulate an optimization problem, which is an asset allocation problem to basically maximize the expected return, subject to some bound on the variance of the portfolio in the constraints. And then what's happening is the person who's solving this optimization problem, trying to determine their portfolio, is using predictions of the returns based on these contextual features to then plug into the optimization problem to make a decision about the portfolio. Okay, so these are sort of two concrete examples in this paradigm of predict and optimize, where we first predict the parameters using some machine learning model based on these contextual features, and then we plug in the predictions into the optimization model to make a decision. All right, so we call this the predict and optimize framework, but there also are several sort of related terms in the literature. End-to-end learning is one of them, also decision-focused learning. These are related terms that generally mean the same thing. And so in this talk, I really want to communicate some work that I have done along with my collaborators that highlights sort of fundamental statistical and computational concerns and results in this framework. In particular, going back to my motivation from before, I want to consider what we call a smart predict and optimize approach here, which somehow takes into account the fact that the predictions are being used as inputs to the downstream optimization problem during the learning phase, right? So when we're determining the model that we want to use, right, the model for predictions, we want to somehow train that model in a way that accounts for the fact that the predictions are inputs to this downstream optimization problem. That's what we mean by smart. So we'll develop sort of a smart approach here, and then correspondingly develop some fundamental statistical and computational results about this approach. Okay, so in particular, in this talk, I'm going to keep things relatively simple and focus on linear optimization problems, so stochastic linear optimization problems. So my problem of interest is this stochastic optimization problem, where really the objective function is sort of a stochastic objective function that depends some context vector, right? So first of all, my constraints S are some given in known convex and compact set. So I assume that there's no uncertainty about the constraints. So you can think in the shortest path example, the constraints represent the structure of the network, and we completely know the structure of the network. So there's no uncertainty about that. Instead, where there is some uncertainty and also dependence on the context features is in the objective function, right? In particular, we assume here a linear objective function with some unknown cost vector C that has some distribution depending on an auxiliary feature or context vector X, right? So d sub X is the conditional distribution of C given this auxiliary feature. And ultimately, we want to minimize expectation of the objective function, the linear objective function, with respect to this conditional distribution, right? So that's the problem that I'll focus on here. Of course, there are natural extensions to nonlinear problems, problems where there is also dependence in the constraints, and so forth. I'll focus here on this simple setting as a starting point, but I just want to mention those extensions do exist. Myself and also others have considered extensions like that. And there are many approaches for dealing with this problem as well as its extensions. Prior to this work, many of them were really not considering sort of the optimization structure within the learning process. So this work was really sort of one of the first to kind of particularly consider the impact of the downstream optimization problem on the learning phase for this particular contextual linear optimization problem. Okay. So I don't have time to highlight all of the related works, but I will highlight some closely related works as they come up. So why focus on linearity? So obviously, sort of linear optimization is a simple problem class. It's actually also sort of fundamental in this situation. Well, I mean, we'll see basically that the linear assumption includes many interesting problems as special cases, including like the shortest path problem from before. But beyond just that, the main sort of intuitive reason why we focus on linear problems, at least as a starting point, is because the linearity assumption gives us this basic property, right? This basic property that minimizing the expectation of the linear objective function is the same thing as minimizing one particular linear objective function where the cost vector is the conditional expectation of C given X, right? So this sort of fundamental identity tells us that in this linear context, it's sufficient to focus on estimating or predicting the conditional expectation of the cost vector, right? So basically, due to the linearity, the name of the game is estimating this conditional expectation. And I don't really talk about nonlinear problems in this talk, but you can think that so in these sort of more general nonlinear situations, there may be some other sufficient statistics that are sufficient to estimate in order to address this problem, right? But here, due to the linearity, it's just the expectation, right? So just the conditional expectation is enough to actually solve this problem. So we can simplify much of our discussion and much of our algorithms to think about different ways to estimate this conditional expectation, right? Okay, so yeah, so basically, that's sort of the reason why we focus on the linear problems, and then that also sort of justifies the approach of predict and optimize, because then once we have some function for sort of estimating this conditional expectation, we can use that to get a prediction, let's call it C hat, that may depend on some context, but I'm just sort of suppressing the dependence on the context here. So given some prediction C hat, we then simply plug in the prediction into this linear optimization problem and then make a decision. And so And that's sort of again justified by this relationship here. So the predict and optimize process that is really followed by decision makers in practice is that given a new feature vector x, we predict c hat based on x, and then we make a decision based on plugging in c hat into the linear optimization problem, right? And I call that decision w star of c hat, right? So w star of c hat denotes an arbitrary optimal solution of this problem. And that's our decision based on plugging in C hat. And then ultimately we incur a cost with respect to the true realized value of C, right? So at the time of our decision, the actual true value of C is unknown, but later we realize that value and incur cost with respect to that, right? So after we travel along our route, we later learn what the real travel times were, right? And we incur cost with respect to those real travel times. And in general, we realize some cost vector C and incur a cost C transpose W star of C hat. Okay, so sort of the key ingredients of this framework then, to summarize, one, we have this downstream linear optimization task, right, described by this linear optimization problem over some convex feasible region S. And to do learning, what we also need is historical training data given to us in the form of pairs of context vectors along with corresponding linear objective function C. Right, so we have a data set consisting of these sort of pairs, and you can think like for us, we're trying to predict C, so sort of the labels of our data are these cost vectors C. We also, if we want to do learning, we'll assume that we have a hypothesis class H of models, right? Candidate models. These are models that are functions from features to cost vectors, right? So they're functions from the dimension of the features r to the p to the dimension of the cost vectors r to the d. And you can think the output of this function is the prediction of our model given the context vector x. And then finally, to do learning, we also need a loss function, right? So we need a loss function L, which quantifies the error in making a prediction C hat when the actual realized cost vector is C. Okay, so those are sort of the key ingredients of the framework, at least in the offline setting. So sort of the loss function then is what I really want to focus on here, because the loss function is where our novelty really comes in, because we want to think about loss functions which sort of cleverly take into account the structure of the optimization task in their definitions, as opposed to more traditional loss functions which just are based on prediction error. So in particular, to motivate this, let me consider the situation where S is also given by linear constraints, right? So S is a polytope, and I drew an example here. And one example of a sort of classical prediction error based loss function would be the squared error loss function, right? So that's the loss function I define here at the bottom, just 1/2 times the 2 norm of c hat minus c squared, right? So it's classical kind of least squares loss function. And what I've shown in this picture is so basically C here, or negative C is this vector pointing like this up top, and so C is the actual realized cost vector, and nearby to C are two different candidate predictions, right? C hat A and C hat B. I drew their negatives here so I can show that they are how they're positioned relative to this cone around this extreme point, this normal cone. So what's also drawn around negative C is a circle which represents the level set of the least squares loss function, right? So you can think this dotted circle basically represents a region where we have equal values of the least squares loss function, right? The level set of the least squares loss function. So from the perspective of the least squares loss function, all points along this dotted circle are actually equivalent, right? They're all equal with respect to this loss function. The loss function does not prefer any of them over any others. On the other hand, though, looking at the geometry of the linear optimization problem here, we actually see that the prediction C hat A is preferable to C hat B, right? Because C hat A is lying in the same normal cone as C, right? Or negative C hat A is lying in the same normal cone. Whereas negative C hat B is lying outside this normal cone. So what this means is that the optimal solution corresponding to C hat A is actually the same optimal solution corresponding to C, which is the right answer, right? So the decision that we want to make ultimately is the one that corresponding to the realized cost vector C. And C hat A actually achieves that decision, whereas C hat B leads to an incorrect optimal solution down at the bottom right. So even though the least squares loss function treats these 2 points, C hat A and C hat B, as equivalent, we know that they're not, right? We know that C hat A is actually better than C hat B. And so we'd like to have a loss function which somehow accounts for that somehow rewards us for having the correct decision. Okay. And we also can tell a similar story in the case of nonlinear constraints. I won't go through the details of the geometry of this example, but it's a similar story, just even with nonlinear constraints, in this case, simple ellipsoidal constraints. We also have sort of a similar story. Okay, any questions before I move on?
Yeah, I have a question here.
Sure.
So in your caption of this figure, this is just one choice of the loss in your training, right? But this loss has nothing to do with your W star.
That's right. That's right. That's the point. Is sort of like classical least squares loss, which is the first thing that people would think of for doing regression, is actually has nothing to do with the W star. So the point is we want to do something better than that, which is what I'll get to
Oh,
next.
okay, okay, I see. Okay, thank you.
Sure. Good. Great. Okay, so let me actually get to that then, right? So how can we actually, do better than the sort of classical prediction-based approaches like least squares? And so the most natural sort of first thing that you might think about and that we thought about is actually just define the loss function to be the error or the regret with respect to the downstream optimization problem. And that's what we refer to as this sort of smart predict and optimize or SPO loss function. Um, it simply measures the regret when we follow this process, right? So remember, the process says you make a prediction C hat, that prediction leads to some decision W star of C hat, and then we incur some cost with respect to the actual realized cost vector C, C transpose W star of C hat. So this loss function, the SPO loss function, is measuring the suboptimality in this process, or the regret in this process, right? In particular, it's looking at the difference between the cost incurred and the optimal cost in hindsight when we later realize the actual cost vector C, right? So this is actually measuring exactly the cost. And in the case of the example here, right, since C hat A is leading to the correct decision, it would have an SPO loss of 0, right? Because its cost is the same as that of the cost of the optimal decision. On the other hand, C hat B would have a non-zero cost because it's leading to a non-zero SPO loss because it's leading to a different optimal solution. So that's sort of the first thing that we might think about, and then given that choice of the loss function, right, it's a valid choice of a loss function, we can think about training a model through the ideas of empirical risk minimization, right? So we simply minimize over our hypothesis class the empirical risk of this loss function on our data set. So there are a few sort of issues then with this. And I think these issues are sort of highlighted best by looking at a special case that we're all very familiar with. So it turns out that this SPO loss is actually a special case of the classical 0-1 loss in binary classification. So this equivalence happens when S is a very simple one-dimensional polytope. It's just an interval between -1/2 and +1/2, and C is supported on just not -1 and +1, right? So in this case, this is a simple one-dimensional special case of our framework. It turns out that this definition of the SPO loss reduces to this classical 0-1 loss of binary classification, which is simply the loss function that gives you a penalty of 1 if you have an incorrect classification, and a penalty of 0, no penalty, if you have a correct classification. And this type of example can also be generalized to multi-class classification, where now S becomes a unit simplex in D dimensions. Okay, so basically, this sort of leads to some issues, and I actually want to come back to that slide in a moment. So this sort of naturally suggests that solving this empirical risk minimization problem with the SPO loss isn't really such a good idea, right? Because in fact, the SPO loss generally will be a non-convex loss function, right? So the 0-1 loss is non-convex. In fact, the 0-1 loss is actually discontinuous. And the SPO loss also ends up being discontinuous in some cases, right? So going back to that polyhedral example, the SPO loss is also discontinuous because you can think the loss function is always going to be 0 whenever we're in this correct normal cone, and then suddenly it jumps to a different value as your prediction leaves this normal cone, right? So just like the 0-1 loss, the SPO loss is actually discontinuous, and so optimizing this function, this loss function over our hypothesis class, even for linear hypothesis classes, will be a difficult problem. Can be shown to actually be an NP-hard problem. So from a computational point of view, this is not such a great idea. So going back to this intuition from binary classification, a really appealing idea then is to replace this loss function with a more well-behaved surrogate loss function, right? So the idea of a surrogate loss function is to somehow approximate the original loss function with another loss function that has better computational properties. And we introduce a surrogate loss function here that we call the SPO plus surrogate loss function. That's defined like this, and importantly ends up being a convex upper bound on the original loss function. So many surrogate loss functions in binary classification and other problems are actually convex upper bounds like this. So I want to give a little bit of motivation for
I'm
where
sorry,
this. Yeah, go ahead.
So
Yeah.
what is a Z star here?
Oh, sorry. The Z star is the optimal value of so it's C transpose W star of C. So it's just the optimal value in hindsight.
Okay, I see.
Yeah. Yeah, actually, it doesn't affect the definition of the loss function because C hat there's no dependence on C hat there. Yeah.
Got it.
Yeah. So let me give a little bit of motivation of where this loss function comes from. So as I said, it's a convex function. The reason it's convex is because this is actually a transformation of the support function of the set S. And in the case of a polytope, for example, it would be a piecewise linear convex function. And where it's coming from is basically in detail, we have a derivation through some kind of dual interpretation of the original loss function. But sort of the intuition, I think, is really given by this picture, which again looks like the picture from before. And basically the intuition is that if the prediction C hat is leading to the correct decision, meaning it agrees with the decision of W star of C, they're lying in the same normal cone. And also the magnitude of C hat is large enough relative to C, then this maximization problem of maximizing C minus 2C hat transpose W, it's the same thing as minimizing 2C hat minus C transpose W, which if C hat is large enough relative to C, then anytime I perturb C hat, or rather 2C hat, by this cost vector C, I'm still going to be in the same normal cone. I'm still going to be making the same decisions. And so my decision W star of 2C hat minus C will agree with W star of C and also W star of C hat, indicating that that we get a cancellation of terms in this objective function. And in fact, it reduces back to the original SPO loss function. So this gives a little bit of geometric intuition of where this loss function is coming from. I don't think this intuition is perfect. There's more detailed kind of derivation based on duality in our paper. I don't have time to get into it. I also want to just point out that this loss function is actually a special case of another well understood classical example in binary classification. So if we go back to this special case of the 0, 1 loss function, which previously we said that the SPO loss is a special case of the 0, 1 loss function in binary classification. For that same example, it turns out that the SPO plus loss, this surrogate that we propose, is the actual hinge loss of support vector machines. So this SPO plus loss reduces to the hinge loss, another sort of classical, well understood example. And in fact, it also has some connections to in multi-class classification. It also has some connections to other surrogate loss functions for extensions of the support vector machine that people have considered before. So you can think about this in some ways as sort of an extension of support vector machines. Okay.
Can I
yeah,
clarify one more thing? Sorry about that.
sure. Yeah.
So here you mentioned the convexity. Is that convex about the C hat?
Yes, convexity in C hat. Yeah. Right. So we want the loss function to be convex in our predictions. That's
It's
the important.
on your first argument, right?
Yeah. But that's all that's needed, right? Because
But it's not to say the convex about the F. Or,
so for example, it's convex in if we use linear hypothesis class like this one, then
okay,
then it'll be convex in our parameters B. Yeah.
I see. I see.
Okay, so yeah, so that actually sort of leads to my next point, which is then, okay, what do we sort of do with this, right? So the idea is we want to replace the original loss function with its surrogate, right? And then optimize the surrogate, right? So we want to solve sort of an empirical risk problem like this, but with respect to the surrogate loss function. So before I get into the empirical issue, then sort of basic kind of sanity check question that we might ask from the statistical point of view is this question about consistency, right? And so consistency here, in particular Fisher consistency, refers to the property that so suppose basically that we actually know the full distribution of our data X and C, right? Let's call this distribution D. So we actually know the full distribution, which is not the case in practice, right? In practice, we will have data. But here, imagine this ideal situation where we actually know the correct distribution. Fisher consistency asks, okay, if we know the correct distribution, and suppose that we optimize the risk with respect to the SPO plus loss, defined with respect to this true distribution, that's this SPO plus risk that I define here, the so-called population version, does that lead to the right answer? In other words, does it lead to the same model that you would get if you had optimized the original loss function, the SPO loss, right? Because the SPO loss is sort of like the one that we care about, right? That's the one that we want to minimize. It's the one that measures our decision error. Instead, we're using the surrogate, so we're replacing the SPO loss with its surrogate SPO plus. Does that lead to the right answer? And that's what Fisher consistency is asking. And it's a sort of property that's been studied again in binary classification and multi-class classification in a lot of other works. And our result here basically says the following. So first of all, we make another sort of ideal assumption here. This ideal assumption says that our hypothesis class H is general enough that it includes the expected value of C given X. So it includes the correct conditional expectation function. And so if which is just a function depending on our distribution. So if the hypothesis class H includes that function, and the distribution of C given X satisfies some properties, in particular that the distribution has a positive density and is centrally symmetric about its mean, then minimizing this SPO plus risk also ends up minimizing the SPO risk, right? So we actually do get the correct answer when we solve the population SPO plus risk problem. And we have some examples that show that either of these assumptions are not strong enough on their own. So we do really need these properties to prove this consistency property. So yeah, so the consistency here, the Fisher consistency, is sort of like ideal sanity check. It basically says if you have full information of the distribution and if the hypothesis class H contains the correct conditional expectation function, then optimizing the surrogate gives you the right answer. In practice, we're not going to be in such ideal situations. So this motivates our development of these risk bounds. And the risk bounds basically are more quantitative versions of consistency that allow you to, for example, account for the fact that you only have a finite data set. And so fundamentally, these questions boil down to sort of this question that can be framed in terms of sort of like epsilons and deltas, right? Basically says that, okay, if I want to minimize the SPO risk, my target risk with respect to some tolerance epsilon, does there exist a delta so that if I actually minimize the surrogate SPO plus up to that level of delta, then that implies that I have an epsilon solution for the original problem, right? So that's a risk bound. It's a more quantitative version of consistency. Consistency, as I defined before, Fisher consistency is basically asking about perfect optimization, right? It's asking if you can solve the problems exactly. Here, I'm relaxing that to epsilon and delta. And so risk bounds like this have been developed before for least squares and other kind of classical surrogate losses in binary classification. Here we consider risk bounds for the SPO plus risk, and our results look like this. So basically, again, under the assumption that the hypothesis class H contains the correct conditional expectation function, and also under these assumptions that the distribution of C given X is has positive density everywhere and is centrally symmetric about its mean, the same assumptions as before. And also another one which says that the distribution is lower bounded by a normal density. Under these sort of technical assumptions, then we can extend the Fisher consistency result to a risk bound, a more quantitative result, which says that the SPO plus risk satisfies this risk bound with delta scaling like order epsilon squared. Right, so we also want to understand here, not only does there exist a delta, but how does that delta depend on epsilon? And here we show that the delta should be like epsilon squared. We also show that this bound is tight, so the epsilon squared cannot be improved, except if we make a stronger assumption on the feasible region. So in the polyhedral case, this epsilon squared bound is tight. It can be improved to O of epsilon if we make some sort of strong convexity or curvature type of assumptions about the feasible region S. So we here, extend the consistency results from before to something more quantitative, which actually is more realistic in practice. Okay. I also want to mention that in sort of another related paper, we also developed generalization bounds for the SPO loss function. These generalization bounds help us to basically connect the empirical risk problem of minimizing the SPO loss to its expected version. And more generally, basically allow us to say when the empirical SPO loss is close to the expected version. For the same reasons as why optimizing the SPO ERM problem is difficult, right? Discontinuities and non-convexities, generalization bounds are also difficult. So generalization bounds do not just follow from the basic literature because of the bad properties of this loss function. So we needed some new machinery to develop these generalization bounds, and I don't get into the details here, but basically, again, in the polyhedral case and also in the strong convexity case, we develop some generalization bounds for this SPO loss function. Okay. So that's kind of what I want to say about the offline setting. I'll give a discussion of the online setting next. Sort of try to keep it to about 10 minutes. But are any questions on the offline setting before I talk about our extensions to the online setting? Okay, so I think I'll skip these numerical results because we also have some numerical results in the online setting that I'll show. So yeah, so then in the remainder of the talk, I want to talk about this online contextual decision making extension, which is joint work with my student Heyuan. So basically, here we're considering a kind of perhaps more realistic or more adaptive version of this predict and optimize situation where we're making decisions over time, and at each time step, we are perhaps using up some resources that are available. And so in this situation, there's a trade-off between immediate rewards that we gain and the consumption of resources. And a key assumption here that we make is that the rewards as well as the resource consumption amounts are not available at decision-making time, but instead can be predicted based on contextual information, right? So just like I predicted the linear cost functions before, I can also predict my rewards and resource consumption amounts based on some contextual information. So you can think like some example applications. Some of them come up in online advertising, but also just going back to the shortest path problem from before, Google Maps and Waze are sequentially over time giving directions to different people, and each time they give directions to people, their decisions about the directions that they're giving have some impact on the actual congestion of the roads, right? So especially if the app is very popular, their decisions will impact the congestion, right? In other words, their decisions will use up some resources that are available. And so there's a trade-off between giving people the optimal route for that particular person versus using up the congestion on the roads, right? So we have this phenomenon of sort of trade-off between immediate rewards and consumption of resources. Okay, let me describe the problem in more detail. So we have some time horizon T, capital T, number of different rounds. There's a decision feasible region script S, and also a consumption feasible region script V. And then finally, there's a concave utility function U. And the idea is that at every time t, we observe a context vector x sub t. We make a decision wt in our feasible set S based on this context, right? So that's sort of similar to before. But now we observe not just a cost vector, actually we observe here a reward vector RT and also a consumption matrix VT, right? And these the pair of this reward vector and consumption matrix follows some distribution conditional on x sub t, right? So so you can think this like feasible region S is sort of like our same feasible region as before. It may represent the constraints on the network, and the consumption region script V represents constraints on the congestion, right? So S just represents sort of the structure of the network, whereas V represents budget constraints on the congestion. And here, the crucial extension is that we have not only a reward vector, but also a consumption values described in this matrix, which depend on x sub t, right? And then ultimately, after we make a decision, we receive some reward and incur resource consumption according to these linear functions, right? So the reward we receive is R transpose W, and the consumption amount is VT transpose WT. Okay, so ultimately then, the goal of the decision maker at the end of the day is to maximize the summation of the reward and the utility of the consumption, and also satisfy the resource constraints, right? And so we formulate this in terms of the average amount of reward and the average amount of resource consumption. But you could also just simply multiply by capital T to consider the totals. It's totally equivalent. So we were basically trading off this amount of the reward plus utility with the constraints on the resources. Okay, so the way that we consider how to solve this problem is through a sort of penalty function approach, right? So we introduce a penalty function on these resource consumption constraints, and the penalty function is simply the distance to this set script v, right? So it's the Euclidean distance to the consumption set. And the reason why we look at this penalized formulation is because then if you consider a potential conjugate, right, you consider basically the primal dual form of this problem by looking at actually potential conjugate of the utility function and also potential conjugate of the distance function. So we assume the utility function is concave, and the distance function, of course, is convex. So when you look at this potential conjugate, you get this representation of the optimization problem, which now exposes basically the linear structure, right? So it exposes the fact that not only is the reward linear in our decisions, but also there is some underlying linearity in the V, the resource consumption amounts, the V average, which depends on these dual variables lambda and theta, right? So this kind of primal dual representation is very useful. It's something that's been considered, in this literature before. But here are well, first let me say, okay, this sort of leads to this natural kind of idea of an online algorithm, which at every time first makes a decision according to solving this linear problem, right? So it sort of solves the linear problem inside of this primal dual representation, and then updates the dual variables using some online gradient or more generally mirror descent method. So basically, you can think about this as sort of alternating between making a decision with respect to the current dual variables, looking at this primal dual representation of the problem, and then updating the dual variables according to online gradient or mirror descent. And so here our main novelty comes in with the fact that we don't observe perfectly this resource vector RT and the reward vector RT and the resource consumption VT. Instead, we observe this context that we want to use to predict these quantities, right? We want to predict RT and VT based on the context XT. And so basically, looking at this linear problem in step one of our online algorithm, we see that really this is something that looks a lot like the SPO problem from before, except now our cost vector CT is sort of adjusted by this other term that depends on the dual variables and the resource consumption, right? So this motivates us to consider an SPO type of algorithm that uses an SPO loss function to make predictions for these cost vectors sequentially over time, and then feeds those predictions into the online mirror descent method. That's the general sort of high level idea of what we're doing. And that's the algorithm that I described here. Basically, we make predictions at every time for R and V, the reward and the consumption, and then we make a decision according to solving this linear optimization problem with this adjustment based on the prediction of the consumption VT and the dual variables, and then we ultimately observe the reward and the consumption VT, and then update our dual variables according to online mirror descent, and update our predictor by using the past observations to do empirical risk minimization for some surrogate of the SPO loss, right? So we consider a surrogate of the SPO loss with respect to this set S, and perform empirical risk minimization to update the predictor function. Instead of the purely offline learning setting like before, here we have really an online setting where at every time step we are learning a new model based on training it according to from um, past observations from the previous realizations that we had. Okay, so yeah, so basically, I just want to give a quick summary of the sort of results that we have. So I won't get into the details of our regret analysis. I don't think I have time, but basically, we have results in two cases. So in the hard constraint case, meaning that the online algorithm stops immediately when the resource constraint is violated, and also in the soft constraint case where we allow violations, but we want to somehow bound the infeasibility, right? So we want to bound the distance to the consumption set V. So we want that distance to infeasibility to be small. And our regret bounds basically compare to an optimal policy which has full information of the realizations, right? So we consider what's called like an optimal policy in hindsight, which is a policy that would have viewed basically the correct distribution of the realizations. So it has this ideal information that we don't have, and we show that we can actually achieve small regret with respect to this hindsight policy. Right, we show that actually, even though we don't have this information, due to the nature of the online algorithm and our proof technique, which combines the analysis of the primal dual method with these learning theory guarantees in the predict and optimize setting, we're actually able to achieve small regret in both of these cases. So I'll skip the details of the proofs and just show some numerics that also justify our approach. So basically, we have some numerical experiments that compare the empirical performance of in this online problems, compare the empirical performance of using the SPO plus surrogate versus the classical least squares L2 surrogate, and also a few other benchmarks, just a simple SAA method, sample average approximation that doesn't use any feature information, and also a benchmark that is the ground truth that is actually the model that knows the correct distribution ahead of time, right? So that's sort of the non-realistic ideal model. And so let me show just actually the example of the longest path. So we consider a longest path example, which is similar to the example that I talked about before, where we want to go from one corner of the path to another. In this case, we want the longest path, so we want to maximize. And so our decision space is the convex hull of all possible routes. And here we have consumption, which is just corresponding to the decision, right? So our consumption here is sort of like the congestion on the network, which is just corresponding to our decisions. And we also have this utility, which penalizes us for having a large consumption. And so these results basically compare different methods, these different methods that I described. So the x-axis represents a parameter in our data generation process that controls sort of the nonlinearity of the function that we're learning. The red and the green show the least squares approaches. The light blue shows the SPO plus, and the purple is this ideal policy which actually has full information, right? So it's not achievable in practice. So what we see is that the SPO plus is able to get closer to this ideal purple policy, which knows all the information. Because it's using the structure of the downstream problem, it's able to more effectively get closer to this optimal policy in hindsight as compared to the least squares L2 classical approaches. Okay, so sort of to conclude this talk, I reviewed in detail this predict and optimize framework that we've been examining, in particular for linear optimization problems where we're trying to predict the cost vectors of some downstream optimization task. I talked about the statistical properties that we would like in this setting, in particular Fisher consistency of the SPO plus surrogate, as well as the stronger risk bounds in certain situations. And then we briefly talked about this online setting where we also developed an SPO-type algorithm. Unfortunately, I didn't have time to give all the details, but we saw some extensions to this online setting. And I think there are many other exciting and ongoing future research directions in this space. I'm happy to take questions now and also offline later. Feel free to send me an email with any questions. So thanks everyone for your attention.
Okay, thanks a lot for the very nice talk.